So you are very famous in China.
Oh,
Maybe next time you come to China, then you work at the street. They, oh, I know you. Uh, oh, they are about 50. Oh, this is mine. This is the dean. This one, the dean of my college.
Ah. Yes.
This is the first time I do this thing.
Okay.
Yeah, good.那个时间已经快要到了，还有1分钟。就是待会儿的话，我首先用英文介绍一下这个 Tim 老师，然后就是 Tim 老师的报告，然后后面的话会有一段时间的这个讨论时间，然后各位老师如果有问题的话，可以就是在那时候打开你的麦克风直接提问。如果你讲话不是太方便的话，也可以把问题打到那个聊天窗口，然后我们报告最后的话，我会看一下那个聊天窗口里面大家有什么问题。好，我们时间大概差不多到了，然后我们就开始了。Okay, good afternoon, everyone. I am Sun Wenjin from the Nanjing University of Information Science and Technology. Welcome everybody to join this academic presentation hosted by me. Firstly, please allow me to introduce today's speaker, Dr. Tim Fisher. Tim is a physical oceanographer with extensive experience in the field. He obtained his doctorate degree in 2001 and has been working as a seagoing oceanographer at Gilman since 2007. His doctoral thesis focused on utilizing the ADCP data for estimating dipycnol mixing. Since then, his research interests have expanded to include studying dissolved gas fluxes and dipycnol mixing in mesosphere eddies and so on. His contributions have greatly advanced our understanding of those phenomena in oceanography. The topic of his presentation today is underway acoustic survey of internal wave shear. Now let's welcome Tim to deliver an exciting presentation for us. Tim, welcome.
All right. Yeah, thank you, Wenjin, for the kind introduction. Good day and greetings from Kiel. So my subject today is how we can estimate internal wave shear in the ocean, in the internal ocean from underway acoustic data from moving vessels in essence. Yeah, this second natural part is, of course, to use this internal wave shear to estimate diapycnic mixing in the end. As an introduction, we follow the way from the vessel-mounted ADCP until mixing in the end. And the first step, and probably the most important and delicate step, is this step from the ADCP current velocity data that we get to shear, which may be from internal waves, which probably is from internal waves in the interior ocean, but not necessarily. So we would see any shear, of course. But we assume it's mostly from internal waves. And the main problem with this first step is to get these velocities and shear data clean enough to really see the internal waves on the background level. So let's say on the Garrett-Monk level, which is very low. Usually the noise is too strong. So the vertical shear spectrum that we expect to see, that we hope to see after post-processing our ADCP data, looks somehow like this. So we have a wide range in the fine scale range. From here, it's from 100 meters to 10 meters. Then we have a roll-off, and on the very small scales, that's the turbulence range. And with the ADCP, we are in the lucky situation that we see the white, the flat part of the spectrum. So the typical wave number range of our ADCP velocity data in the vertical is about the very convenient range here. And we use the spectral level, so the power spectral level, which is called here a phi S. We use it as a measure for the shear energy of the internal wave field. So here on the left panel, we see again the theoretical shape of this spectrum on the fine scale. And we see that for different shear energies of the internal wave field, we get different levels of the power spectral density. And this is why I chose to define a Garrett-Monk level, so a shear spectral power measure that is easy to handle because the numbers are low. So it's just the multiple of the shear energy compared to the Garrett-Monk level. So G equal 1 just means shear spectral power on the Garrett-Monk level. And here on the left, we see that the spectrum remains flat, so we can still use our Garrett-Monk level now to characterize. Thank you. Thank you for the mouse. To characterize the amount of shear energy which is in the velocity field. But as soon as we come to very high Garrett-Monk levels, there's the risk that we get into that roll-off part of the spectrum. And this is usually about a Garrett-Monk level of 10 or more that we get into a bit of trouble, and in the end can't really see any difference anymore. On the right panel, you see observed spectra in the range of the ADCP, and you see it's for at least for Garrett-Monk levels until 6, it's more or less white as expected, and here for the highest energy level we may see the start of the roll-off, but it's still usable to estimate shear spectral energy. The way from shear to turbulence is well researched. We can see it in simulations, in lab experiments, and in observations. The way is here from the right to the left. So we have shear, vertical shear in any case here, which develops into instabilities and generates further instabilities until we are in a turbulent regime. And this is what we use because there's a relation between shear, the fine-scale shear, and WOPS and turbulent mixing. So we measure turbulent mixing in the field as well, not just the internal wave shear. And this is how we do it. So that's the microstructure probe here with the airfoil tip. And when this probe sinks through the water on a loose cable, then we more or less record the lateral movements of this tip. So going through a turbulent field like this, we end up with profiles like this. In the end, we can generate an estimate of the rate of turbulent dissipation, which is a measure for mixing. So this is a log scale here, and the lowest mixing that we can record is 10 to the minus 9 watts per kilogram, and that's the equivalent to one usual kitchen mixer put into a very large volume of water of 1 kilometer cube length. So the good thing is that there's a good relation between fine-scale shear from ADCP measurements and the microstructure ground truthing. And so we are in a good situation that we don't have to rely on the very tedious and time-consuming microstructure measurements only, but we can complement these measurements by very many independent extra estimates of turbulent dissipation just by going there by ship, and not we don't even have to do stations for this. And so here is an example. What we did with that is a seamount mixing study. This is West Africa here, the Cape Verdean Islands. And here's a seamount range, which shows in the upper 500 meters enhanced mixing, about a factor of 3 higher than in the abyssal surroundings here. This was only possible due to these ADCP estimates of diapycnal mixing. And if we look at the vertical profiles, this is done by a microstructure probe, of course, because we can't do profiles by ADCP estimates. It's only one value per profile that we get. So in this case, we had some microstructure profiles to check for the vertical structure, and it's for the top 500 meters, we end up with a factor of 3 that we got from ADCP as well. But we see that going deeper and coming to the tops of these mountains, that the C-mount induced mixing gets even stronger to a factor of 10 or more. So just as an example. And now we come to the technical part, to the important first step to get clean shear data from the ADCP in order to do all this work. There's several issues with that. So we have losses of velocity variance that we measure because the ship is moving over the internal waves. We have velocity losses, variance losses, sorry, because the ADCP is working as it is. So essentially because it's the data are binned into depth cells. We have measurement noise, of course, and we have some extra issues sometimes because of scatterer inhomogeneity in the water column, which is mostly due to the diurnal migration of the zooplankton. And sometimes we have issues with ship techniques because on station there may be a pump set or something which deteriorates the data or even destroys the ADCP data at all. But the good news is that we can do something about it. So there's some measures to counteract these variance losses and to reduce the noise. So it's mainly in 3 steps. So we do averaging over very short time scales just to avoid these variance losses of the first kind. Then we do filtering to reduce the noise. And in the end, we correct for all the variance losses during the ADCP data assembly and during all the post-processing. And then we have to deal with these special issues of during cruising or during station. So to put it in a nutshell, let's say this is what happens to the ADCP recorded velocities when we do all these steps here. So we record single ping velocities in the beginning, and the noise is so high usually that we can't see anything. And then we do some little time averaging and see that some structures are rising here. And we are already in some noise range, which is kind of okay for usual for the usual use of the data, but then we need extra low noise, and this is why we do the filtering of the data. And you see it already looks very smooth, and the noise level is really low. And in the end, from these clean velocities, we get spectral estimates, and these spectral estimates have to be corrected for all these variance losses. And so we have here a corrected, some example of a corrected spectrum, just a 1-minute spectrum. That's why it's not looking very white, but in the end, at least we can estimate the GM level from it. So it's about twice the background internal wave level here in this example. Okay, we go through these 3 steps a little more intense, let's say. So the variance loss due to the ship movement. So when you look at the left panel, you see that the less the less you average during your cruising, the less variance you will lose, of course, in the horizontal, even or in the vertical. So the vertical shear itself, the vertical shear energy itself, is affected by this interval of averaging directly. So on the right panels, you see that on if we are on a station and not moving, it doesn't matter much which averaging interval you choose between 1 or 30 minutes. But when you're cruising, it matters a lot. So averaging 30 minutes would mean that we lose most of the shear energy that we can record just through all these vertical wave numbers, especially the short ones. So to keep these losses at a minimum, we always try to stay at 1 minute averages. Then the second step is the two-dimensional filter. So it's in the domain of time and depth. That's how our ADCP rockets are. And we see that the distribution of signal and noise is very peculiar from internal waves. So the theoretical Garrett-Monk spectrum on station looks like this on the lower left panel. And if we are moving at 10 knots, I think it gets distorted. And in our observation, it looks about the same. And we see that the noise is mostly concentrated in these corners of high frequencies and high vertical wave numbers. So we make use of this and create an optimum filter, which looks like this in this case, but it depends on regional parameters, on the ADCP bin size, on the noise level that we have. So for every cruise, we have an individual optimum filter. And this is the difference you can make by using this filter. So in the end, we have to compensate for all, oops, I'm sorry. We have to compensate for all the variance losses we have piled up so far. So it's from the ADCP, the technical smoothing, and from the filtering, of course, we have smoothed again, because we not only lose the noise, but also lose parts of the signal. So for an example, we just put here as the assumed true field of shear, we put just a Garrett-Monk spectrum of level 1. And just when we simulate what happens when we do ADCP measurements, we see that we have here the technical losses, which would reduce our spectrum to the high wave numbers. And then we add noise. And in total, we end with a measured spectrum, which is much above the true spectrum. This is not desirable, of course, and this is why we do filtering. And when we filter, we not only reduce the noise to this curve, but we also reduce the signal to this curve. But in total, we end up now below the true spectrum, and we now have the chance to first to measure such a low shear spectrum at all, and on the other hand, we have a key to compensate for the spectral losses. So we just take these factors here between these two curves for correction. Yeah, so theoretically we're done, but there's still those special issues. So one is caused by scattering inhomogeneity, and added with the fact that the ship is moving above it. So this is just a typical backscatter from the ADCP here. Obviously, we are at dawn because the zooplankton is going downwards to 300 meters. That's the strongest signal here, but there's also some inhomogeneities at other places. And when we look at the vertical change of this curve, of this plot here, we see some patterns. And okay, for reasons that are too long to explain here, these vertical gradient of the target strength is copied somehow into the longship velocity. So we can really see this pattern, not only the strong ones, but also the weaker ones. We can really see it in the longship velocity. And it's only in the longship velocity, so the across-ship velocity is clear from that. So there are other disturbances here, but at least there's not this pattern here. And that's the only cure we have for this problem. We have to rely on the across-ship velocity, because these patterns here are so strong and we can't really eliminate them. And these patterns are just on the vertical length scale of internal waves, which we see here. So that's a histogram of from 2 cruises, and it's the statistics of all the Garrett-Monk levels that we recorded, split up into a cross-ship velocity and a long-ship velocity, and split up into station, work, and cruising. And we see that all these distributions are very similar. So our cross-ship velocity doesn't care for station or cruising. It's always the same distribution. And if we are not moving, of course, the longship component of the velocity is also okay. But when we are cruising, the longship component is a factor of 3 higher at least. So that we want to avoid. Yeah, but we can cure this longship velocity problem during cruising, so underway. And it would be nice if we could just use the station data as they are, but in practice, and depending on the ship, we have problems on stations as well. So in this case, on this particular ship, we had a pump jet near the ADCP position in the hull. And when we were on station, it was used heavily to keep the ship in place. So this was during those times here, and we see the effect. So the velocity data are more or less destroyed during these times, and this will generate, of course, very incorrect estimates of internal wave shear. So we can only use stations where there's no such disturbances. And sometimes we can, for stations, we can use the adjacent times when the ship was nearing the station or going from the station. That's a workaround. Yeah. So we're at the end. So instead of a summary, I again show this this workflow here. And yeah, in the end, it's not just a matter of post-processing, of good post-processing to get to the internal wave shear, but of course we have to do thorough quality control to get rid of those along ship problems and the station problems. Yeah, thank you for listening.
Yeah.
Questions?
Okay. Thanks, Tim, for give us the report. So, next step is the question. If anybody have the question, you can open your voice and just ask.
Okay, this is Changming and from the Nanjing University of Information Science and Technology. I'm the colleague of the Wenjing. Thank you, Tim, for the presentation. Can you hear me?
Yeah, I can hear you. Thank you.
Yes, it's a interesting talk, and I have a couple of questions. So first of all, I would like to congratulate the Wenjing for his promotion to the associate professor just last week. So congratulations to the Wenjing.
Thank you.
Okay. Yeah, it's a good news for him and for his career, development. And so for your presentation, I have a couple of questions. The first of all, you have the slides show this enhancement of the mixing over the seamount, right of the Peru coast, right? And that's a Peru coast.
It's a West African coast.
West African, yes. West African. Okay, so that's enhancement. It's a very distinctive. It's very outstanding. So, do you have any idea? So, what caused this enhancement of the mixing over the seamount?
Yeah, it's most certainly it's internal tides at the flanks of the seamounts, which cause the enhanced internal waves. So those seamounts have their tops at about 1,000-meter depth.
100. What depth of the top of the seamount?
1,000. Usually
1,000. Oh, it's a very deep, deep sea.
Yeah,
seamount.
some are at 300 maybe, but most of them are 1,000-meter depth. And it seems the internal waves don't just stay in this depth, but influence all the water column.
Yes, it's 100 meter, 1,000 meter. It's quite up below the thermocline, the picnocline, right? So, so that's that could cause some condensing. Yes, maybe it's internal tides. Okay, so this data. So what's this? You get the diffusivity and the shear. Because there's another question come to another question. So you measure the half part of the presentation is about how the processing the ADCP data get the seamount or get the shear, the shear, but the shear is not, it's when you look at the diffusivity, the turbulence model, the shear and the density gradient, it's together come to the perimeter. That's affect the diffusivity. It's not only the shear, it's also the density, the profile. It's also important. So that's you along with the ADCP data, do you have the CTD come with the ADCP data? Also, you get the density vertical gradients there.
Yeah, we had during these cruises, we had probably 100 CTD stations or something. So I could generate a field of density gradient below the thermocline. So these ADCP data are used between 150 meters and 500 meters. And we had a very linear stratification there. So I could just use one stratification value for the entire spectrum.
Okay. Right. So that's it's a shear. The vertical shear definitely important for the turbulence mixing, but when you get the diffusivity, so you apply some turbulence model to get the diffusivity, or you just consider this shear is caused by the turbulence, by the internal wave using the you. So my question is, how do you get the shear when you measure the shear? How do you get the diffusivity? So you apply some new, you show some the scattering plot, but so you get that direct question is, how do you calculate the diffusivity from the shear? So you apply some turbulence model there or no? Yeah.
So I use the data that were used for the fine scale parameterization of Polzin, Gregg, and Henier.
Oh, okay.
These are the hollow symbols here, and I checked with my own ground truthing from microstructure for the fine scale parameterization. So, and the relation is so good that we just used it. So we come from ADCP shear and the stratification, we directly come to estimates of epsilon, so of turbulent dissipation.
Yeah.
And from that, we go by the Osborne relation to.
Osborne, that's 1980. That the permit.
Yeah.
That's equation. Yes.
Yeah.
Okay. Yes, I got it. So that's Western Africa. That because I have the graduate students working on the seamount induced mixing. I'm not sure we can to use your data, Western Africa, the seamount data to check out some of our calculation. We using the numerical model to estimate how the seamount, the presence of seamount to enhance the vertical mixing. So we lack some, the observation data to validate our results. I'm not sure your data is can share with us or not. Just this extended question. Yeah.
Yeah, I guess so. Would be nice to cooperate. Yeah, sure.
Okay. So that's my question. Thank you so much for your presentation.
Yeah,
very interesting. Okay. Yeah.
Okay. If anybody have other questions?
Hello, many thanks for your report. I'm Fenfen Liu from Sun Yat-sen University. It's very interesting and useful report and many inspiration for observation. We are pleased that this report also provides a learning opportunity for staff in southern Marine Science and Engineering Guangdong Laboratory, Zhuhai. And also congratulations to Wenjin. I I have a question that I face. In fact, I faced a question recently. There are a lot of noise in the observation.
Yeah.
I don't know in the depth of near 100 meters in the upper ocean, how to distinguish sub-mesoscale and other forcing factors. Thank you.
Yeah, thank you. It's just the, oh, sorry, I'm searching for this slide. It's just the assumption that in these very high frequency and high wave number parts of the spectrum, we only find the white noise of the instrument and of the measurement procedure at all. So the internal wave signal condensates somewhere in the middle here. And probably mesoscale movements should be even on lower time and space scales, and it should be even more inside here. So, but it's just an assumption that we can get rid of the white noise, which is due to technical reasons.
Thank you. Thank you very much.
Okay. Does anybody have questions? Okay, if you need more time to think, then I ask a question. If I would like to compare the velocity, shear, the energy, compare from the ship moves and the stations. So I calculate each other, and for the stations, the method is doing well, and we needed to divide it into the along shape and the cross shape. But when the cross is moving, we only can use the cross shape date. So the energy is not the all of the energy from the shape move. Yes. So
yeah.
So if we lost a part of the energy, so the shape moves energy and the station's energy, they can't compare or something.
Yeah, that's right. So we essentially don't know what the along ship component will be, but the assumption is that we can just take twice the across ship energy.
So we assume they are the same.
Yeah, we assume that they are statistically isotropic, or whatever you may call it. Yeah.
Okay. Yeah, then another question is at the CTT station, the ships not move. So the across and along, how to divide out them? Which is along, which is
it doesn't really matter. You can use the along ship component, which is just in the direction of the heading, and calculate the perpendicular part as a cross ship component, or you can even use zonal and meridional velocity.
Okay.
That on station it doesn't matter. Okay. Only has to be perpendicular.
Okay. Okay. Yeah. Okay, Anna, thank you. So anybody on the line have the questions? Okay, last 10 seconds. If there have no question.
You could write an email, of course, if you think later of something that wasn't clear.
Sorry, I have another question. Why C-mount intensify the mixing?
The C mount?
Yes, why C-mount intensify the
That's
mixing?
probably due to tides that break at that turn into baroclinic tides on the flanks of the seamount, and then generate these breaking internal waves. Not necessarily directly at the seamounts, but there's some here it is. So it's not necessarily directly at every flank of every seamount, but there's regions where it's enhanced, and these regions are not even necessarily completely near the seamount, so there's some remote mixing as well. And obviously it's not confined to the depth of the seamounts, but the internal tides, internal waves are also going further up.
So did you measure the phytoplankton? Did it cause some phytoplankton bloom?
Sorry, I didn't understand.
Oh, I don't know whether you measured, you have some phytoplankton observation. Did it
No,
bloom?
no,
Oh,
no,
okay.
I didn't look at that. I don't know of any reports that there would be much more chlorophyll in this region than outside, but then there may be some signal, but I don't know of. Sorry.
Oh yes. Okay. Thank you. Thank you. Thank you.
Okay. About this work, Tim just write at his doctor thesis and didn't publish the paper for this work. Yes.
Yeah.
Maybe in Germany, the paper is very important, but not so important as in China. So this work only at his doctor's thesis. If you have any questions about this report and about this thesis, maybe you only can read the thesis note and open publish the paper. So Tim, could you give us the email?
Oh yeah,
address?
sure.
Yes.
Sorry,
So,
I should have done before. Oh, what is this?
maybe I need to change the.
Oh, I see.
H Gilmore?
Yeah.
No. Okay.
So your thesis is written in English, right, Tim?
See, this is in English, yeah.
Okay, good, great.
So only missed the H.
So it can be found in a public domain.
Sorry.
Yeah.
They
Most of the
say,
theses can be found on the public domain.
yeah.
So if you can, okay, great.
Yeah, you should be able to find it when you forward.
You're welcome to visit our university in future.
Oh yeah, thank you.
Yeah,
So
and the Martin is my co-advisor of the PhD at Columbia when I was there. Martin Wisbeck.
Ah, great. Yeah.
Mhm. So Martin has known me for more than 20 years, more than 20 years. Okay.
So this is your email. Just we missed at. So we
Yeah.
there only need at, then the email is right.
Yeah. Yeah.
Okay. Okay.
All right.
The keyboard it's the German keyboard. So here we only lost the at, and then the email is correct. Okay.
Thank you, team. Thank you, Wenjin, for the seminar. So
Yeah. Thank you, my team leader, my teacher, Professor Dong. Okay, if there still have some questions, you can send the email, or you can send the email to me or to Tim. Okay, then today is let's thanks Tim for give us a report again. Okay.
Thank you.
Then
Thank you, both of you.
Thank
yeah,
you for
thank you.
listening.
So this is finished. Okay, bye.